Hi, video 14-3, deviation from calculation. So, deviations from calculated values, meaning when we calculate things like delta TF and delta TB, changes in boiling point and freezing point. Okay, so suppose I give you three solutions. One is sugar, one has KCl, one MgSO4, and one barium chloride. Should the delta TF for all three of these solutions, all same concentrations, be the same? Okay, now remember, delta TF, the formula is going to be Kf, the constant, times the molality times I. Okay, so they're all three solutions, same M. They're all going to be in the same solvent, water, so Kf will be the same. Only difference is going to be I. Okay, so what's I for sugar? Okay, non-electrolyte, so that's 1. Okay, I for KCl should be equal to 2, right? Because KCl, this will break up into K plus and Cl minus. Okay, what about the MgSO4? Well, Mg2 plus and SO4 2 minus. BaCl2, this, well, let's do it up here, breaks up into Ba2 plus Cl minus. When you balance it, since that's a 2, you need 2 of those. Okay, so I for MgSO4, you get 1 Mg plus, 1 SO4 minus, so that should also be equal to 2. And I for the BaCl2 is going to come out to be 1 plus those 2, so it comes out to be 3. So should the delta TF be the same? No. Okay. But if you want to compare the delta TFs, okay, for the KCl, it should be twice as big as what the sugar is, because I is for 2 for KCl and only 1 for the sugar. And the delta TF for the KCl and the delta TF for the MgSO4 should be the same, because I is 2 for KCl and I is also 2 for MgSO4. Okay, now we actually go and make a solution of 0.1 molar of all three of these things and go measure the delta TF values. Okay, and for sugar, we expect that it should be 3 times as large as, the BaCl3 should be 3 times larger than the sugar, because I is 3 for the BaCl2. Okay, now when they actually go and measure the delta TF values, okay, it turns out that sugar isn't twice as big. It's only 1.85 times as big as the KCl, meaning I for KCl is actually only 1.85 and not 2. Okay, for the MgSO4, you say, well, that's pretty close to 2, but MgSO4, it's the same I value. Okay, but for MgSO4, the I value actually, the real I value comes out to be only 1.21. Okay, so we don't get 2 moles, we only get 1.21 moles for every 1 mole of MgSO4. Okay, and for BaCl2, we thought it should be 3. I only comes out to be 2.53. Okay, so why do these substances have less of an effect on the freezing point depression than expected? Okay, it doesn't go down as much. The sugar, the TF should have made it go down twice as much as the sugar, and MgSO4, you should say, well, it should be exactly the same, but it's even smaller. Okay, so why do we have a smaller effect? Okay, well, take a look. Basically, what's happening, we expect I to be equal to 2, so 1 mole should give you 2 moles. Okay, so let's say you get A plus and X minus. 1 mole of that and 1 mole of that, if you have something that should give you 2 ions. Okay, but what's happening? We're assuming all of this breaks up. And in reality, okay, some of the ions do not totally break up. They still experience an attractive force between them. So not every single one of the AX or the NaCl or KCl or whatever things we're talking about don't break up. Okay, unless the solution is really dilute, the more dilute you have, then the farther apart these ions will be, and the greater that they'll break up. In other words, the less chance that they'll actually start sticking together. Okay, so in other words, the ions are not as free to disperse as we would expect them to be. Okay, now why did the MgSO4 have a different charge than, or have a different I value, actual I value than the KCl? Okay, MgSO4 breaks up into Mg2 plus and SO4 2 minus. The KCl only broke up into K plus and Cl minus. Okay, so we should still get 2 particles and 2 particles, but the plus 2 minus 2 has a greater attractive force than the plus 1 minus 1. So the larger the charges in the ions, the stronger the attraction is and the bigger the deviation from the actual I value. Okay, so here's your review question.